Okay, so these tips and tricks are mostly going to be applicable to smaller multiplication questions, or to ones that are rather unusual. You wouldn't just pick an a times b, two randomly selected 5-digit or 8-digit numbers, and try to use these techniques. But the first technique is the one that's most widely used, and it's just using complements. You likely do it naturally already when doing smaller multiplications. For example, if I need to multiply 9 times 73, um, you could choose to multiply, 9 times 7 plus 9 times 3, or you could simply do 73 times 10 minus 1 times 73. Um, you know, maybe that's not the best example, but it's something that you would use commonly just naturally. When you're using the complements, you're doing the school method, but you've modified it, rather than multiplying with the numbers that are present. You've changed it to try to make it easier. Um, it requires you to use additional visualization. So in a typical school method approach, you are multiplying with digits that are written down or that you can see. You visualize the number and then you work with the digits. If you're going to use complements, not only do you need to visualize the number you are given, but you're also going to have to visualize the number you've changed it to, or keep track of what you've done to change it. The most difficult requirement of using the school method is the visualization required. So using complements and making the visualization even more demanding is going to be difficult. It's going to have to be a question that is clearly within your school method ability. A 1 by 1, a 2 by 2, a 1 by 1 by 3. But trying to use a complement for a 5 by 5, if you're not a Soroban expert, is likely going to be difficult. And again, as I mentioned earlier, it often going to be naturally applied when you're doing smaller calculations. A better example than what I gave before is if you need to multiply 167 times 59, you would probably do 167 times 60 minus 167 times 1, rather than doing 167 times 5 and 9. So here's an example of using complements on a larger question. And so we have 1665 times 3,491. So here what I've done is I've deconstructed the number on the right. We're going to do 3 times 1665, which is 4995. Now, rather than working with the 491, I'm going to turn that into a 500 and a minus 9. So I'm going to take the 5, multiply it by 1665, and come up with 8325, and then take the minus 9, multiply that by 1665, which is 14985, and now I add in the zeros at the end of the numbers, and complete the question and come up with 5,812,515. So as you can see, when I'm doing this, I have to make sure that I'm confident in how I've changed the question, and I also have to be ready to do addition and subtraction instead of just addition. When I've added these first two numbers together, 49,950 and 8,325, now I need to be confident in adding the zero and subtracting the 14,985, which, depending on your experience, may be difficult. A second trick that can be used to solve multiplication questions is to factor out the numbers. This takes advantage of the observation that A times B times C is the same as A times B times C. Okay, so what do I mean by that? I mean 7 times 77 is the same as 7 times 7 times 11. You do not need to break the numbers into prime factors. You can simply break them into composite factors, or whatever factors you think it's easiest to work with. For example, the number 50, if you're doing it naturally, could be broken into 5 and 10. You could break up 75 into 5 and 15, or 5 and 5 and 3. Those are primes, but whatever makes it easiest to work with. Um, this can be extremely useful for medium-sized questions, um, or for doing questions when maybe you don't need to do it rapidly. Um, it's also extremely useful for multi-operation questions when you're struggling with the visualization component. If you need to multiply three numbers together, breaking them apart and multiplying it by one digit at a time keeps that in your mind, um, and makes it easier to remember it and continue working with it. Now, the challenge with using the factorization method is that you need to be very quick in breaking that number up into different factors, and you need to make sure that you've remembered what factors you've previously applied. So here's one very easy answer. This is 216 times 343. This is also 6 cubed times 7 cubed. So doing this, the school method, or the cross multiplication, not so difficult. But if I see those two numbers right away, and I know 216 is 6 cubed or 343 is 7 cubed, I can actually do this question rather quickly as well. I can take 216 times 7 and come up with 1512. I can multiply that by 7, come up with 10,584, and then I can write 74,088. Um, wasn't particularly difficult. I could go the other way and break 216 up into 6, 6, and 6, and I could multiply those by 343. I could even double, I could break up those sixes even more into 2 and 3, and do it like that. But you can see when I'm doing this, unlike school method, I'm not really going to have to visualize that much, or perform, at least visualize and perform additions with the number I've visualized. Instead, I'm just creating an intermediate answer and then updating it until I have the final answer. Okay, so here's a much more difficult version. Now I've taken 216 and 343, and we're going to multiply it by a new number, 874. So this is obviously a challenge, but doing this question, 874 times 216 times 343, is going to be a challenge in general. So here I'm breaking up 216 into 3 sixes, and I'm breaking up 343 into 3 sevens. I'm going to take each of those sixes and multiply it by 874. So I'm going to come up with 5244, then 31464, then 188784. And now I'm going to have to multiply that 6-digit number by 3 sevens, 1321488, 9250416. And once I get to the end, I can write down the digits as I go, either right to left or left to right, and come up with the final answer of 64,752,912. But again, the advantage here is that I'm when I'm building the number as I go, the number is easier to remember. I'm just visualizing one number here. I'm not performing any additions or subtractions. I'm just updating the intermediate result as I'm going. Okay, so the third trick I'm going to explain is the use of squares, or more accurately, the use of certain algebra to change the question into something that's easier to work with. So, for instance, here is 63 times 37. Now, I have picked these two numbers because they are both 13 away from 50. Using the formula that was displayed on the previous page, 63 times 37 is equal to 50 squared minus 13 squared. The 50 being the midpoint of the two numbers, and 13 being the difference from 50 for each of 63 and 37. So 63 times 37, using the school method, you might very quickly be able to come up with 2331, but there's actually a good chance that you would be able to notice that 2500 minus 169 is 2331 as fast or faster than if you try to do the school method. Okay, but I do not need to take the midpoint between the two numbers and in order to apply that formula. I can use a modification of it and use it to apply it to any two numbers. So here, 208 times 272. Now I can move down 8 on 208 and come up with 200. And then I can move up 8 for 272 and come up with 280. And instead of 208 times 272, I can do 200 times 280 plus half of the difference between those numbers. So 200 and 280 are 80 apart, divided by 2 equals 40. And I take 40 squared, I add it to my answer, and then I subtract half of the difference between the two original numbers. The difference between 208 and 272 is 64, so that is 32 squared. And I get 5600 plus 40 squared minus 32 squared. So 40 squared minus 32 squared is 576. So my answer is 56,576. So to take an even more complicated example, here I have 338 times 873. Now I'm going to need both of the numbers to either be even or odd, but I can fix that just by changing it to 338 times 872 and then keeping 338 and adding it to the answer of 338 times 872. Now for 338 times 872, I'm going to move up 28 for 872 and down 28 for 338 and come up with 310 times 900. This is the little bit a difficult part here. Now I have to take half of the difference of 900 minus 310, take half of the difference, 295, and then take half of the original difference. And now if you notice here, the original the difference between the new half of the new difference and half of the original difference is just how much I moved. So 900 minus 310 divided by 2 is 295. I moved up 28 and moved down 28, so the original half of the original difference is just 267. So now we have 310 times 900 plus 295 minus 295 squared minus 267 squared. Well, so this looks pretty difficult, right? 295 squared minus 267 squared. But actually, we can find the difference of the squares using another formula. And this formula is simply that the difference is 295 plus 267 equals 562 times 295 minus 267, which is 28. So in this case, we have 310 times 900 plus what we actually have down here is how much we moved up and down, 28. Then we have the original difference between 338 and 872, which is 534. And we have 534 plus 28 here. So by moving up and down 28, we can turn this question into 310 times 900, a relatively easy question to solve. Then we need to add to it the amount that we moved up and down times the original difference plus the amount we moved up and down. So 562 times 28. So I've written out the steps to get there, but really you could immediately move. You don't need to think or write 295 squared minus 267 squared. By moving 28, you should be able to quickly come up with 562 times 28. Now, this didn't make the question that much simpler. I've turned a 3 by 3 into a 3 by 2 and this 2 by 1, which isn't that much simpler necessarily. But when I look at these numbers, this appears to be a much simpler calculation. We just have 31 times 9, and then we have 562 times 28. The 3 by 2 is generally going to be much easier to do than the 3 by 3 if you are a non-Sorbonne competitor and you don't have a extremely highly developed visualization ability. So I have 297,000. The result of 562 times 28 is 15,736. I need to put the 338 back in there that I took out earlier, and we come up with our answer, 295,074.